And let me just show you this. This is one of the sorts of supports that string theory has. And I should say it's got nothing to do with physics as far as I can see, but it has an amazing effect on mathematics. In fact, what I'm going to do at the same time is I'm going to put a quote over here. I don't think I'm going to take the time to read it here. This is just a quote from Ed Witten, who is sort of one of the prime mover, I suppose, in modern string theory, and Richard Thomas, who's a very excellent mathematician who's been influenced by it, and I just think this shows that the sort of impact that some of this work has had on mathematics, and it's this sort of a thing. Let me just tell you what this is. There's a certain problem, I'm not going to describe the problem, which a couple of Norwegians, these people here, I won't even try to pronounce their names, were trying to count certain things called rational curves on a certain space. And they came up with a certain class of spaces, I should say. And they came up with these numbers here, you see. And the string theorists, using something called mirror symmetry, which is a very clever idea, which at the time nobody had proved, it was just an idea, which comes out of, it's the sort of thing that Thomas is talking about here. It's just a conjecture, at least it was originally, and these same numbers come up here and here, and then a different number. And so the idea was, look, okay, nice try, but it's not right, you see. And then the mathematicians went away and found an error in their computer code and came back again and said, whoops, you were right. It was this number. And then the physicists, this is my colleague Philip Candelas and some of his associates, said, well, they had a much simpler way of calculating the numbers using this mirror symmetry, and they got all much bigger ones. They could just keep on going like this. Whereas these are far, far harder, these techniques the mathematicians did. So there's something deep in what's going on here. No question there's something deep there. But what's not clear is that it's got anything to do with physics. It might be just deep mathematics. And there's no question but that Witten here is a very profound mathematician. He's also a physicist, and he takes the view that what he's doing here is probing the secrets of nature, and that was what led him to insights. So there's something going on behind the scenes, that's all I'm trying to say. It doesn't mean that it could even be something deep to do with physics, but if it is, it's not quite what the string theorists think. That would be my view. Okay, now I want to say something about the last topic, and I hope I still have some positive minutes, I'm not sure. I can't see the clock, and anyway, we wasted time moving rooms. Oh, there's one there, oh yes. Yeah, that's not so good, is it? I was trying to use the excuse I couldn't see the clock. But I think, well, I didn't start until quite late, so let me go on for a bit. I want to say something about the last one, the fantasy. Now, you see, the thing about this, I really want to take a slightly different take on this. It's partly because things have changed in my understanding of various things. Okay, it's fantasy, that's true. This was fashion, yes, that's true. This was a faith. Quantum mechanics holds at all levels. There's no real reason to believe it holds at all levels. It's a faith based on a lot of very good evidence, but not evidence of the nature that allows you to extend to all scales. Fantasy, well, surely that shouldn't be anything to do with physics, should it? I mean, that's fiction or what have you, fairy stories and all that sort of stuff. However, there is something very, very odd about the way the world is constructed. Black holes, they're odd enough. The fact that they sometimes shoot stuff out at nearly the speed of light. There's one example where this black hole in the center of a galaxy is squirting this stuff out at another galaxy, as though it was a sort of Star Wars going on out there. So yes, it's fantasy out there. The biggest fantasy of all is that this entire universe of ours is supposed to have started in this great whacking, great explosion called the Big Bang. Well, what about the Big Bang? There's a lot of evidence for it. And one of the most striking pieces of evidence for it is what's called the microwave background radiation, which is sometimes referred to as the flash of the Big Bang. It was discovered by accident, although it had been predicted by other people that it should be there. This radiation should be there. It's coming to us from all directions, pretty well uniformly over the whole sky. And it has this very remarkable spectrum. You've seen this in the previous transparency. The continuous curve here is the Planck curve. The little lines here are the error bars. The temperature of this radiation is something like about 2.7 degrees absolute. That's above absolute zero. And the error bars, you see, are indicated here. Well, you see the error bars are actually exaggerated by a factor of 500. So if you squash them down by a factor of 500, they would simply hug the curve. Even the worst one to the eye would be right spot on. So there's something extraordinary going on there. What is that curve telling us? It's telling us that what you're looking back at is what's called a black body spectrum, which is thermal equilibrium. Now, to explain about that, I shall have to say something about the second law of thermodynamics. What's it all about? Entropy and things like that. The second law of thermodynamics tells you, roughly speaking, that things are getting more and more random as time goes on. Well, I want to be a little bit more precise than that. Here's the sort of cartoon with a glass of wine perched on the edge of the table. It gets jiggled and it knocks off, and the wine spills into the carpet, and the glass breaks, and so on. And this is all to be considered as something, say, Newtonian mechanics, which is time symmetrical, and so all the particles are behaving according to the precise laws of Newtonian mechanics. Those laws are completely symmetrical in time, so if this is possible, then this is equally possible. So why don't you ever see that in that order? Well, the usual answer people give is that there's a thing called entropy, which is a measure of the disorder in a certain sense, and the second law tells us that the disorder increases with time. Well, I want to be a bit more precise and give Boltzmann's definition. Now, you see, remember, this is phase space. We've done phase space. Phase space of the situation in this room here. Now, when the glass is at the top here, say, there will be lots of different ways that all the air molecules could be different places, different motions, and so on, as long as on the large scale they're the same. So if the pressure and the density and the velocity of the gas and everything is the same, then the different ways that each molecule may be moving, there are loads and loads of different ways they can do it, and let's consider that the configuration here is represented by that point. And all the different ways, which look the same as that, have the same temperatures, the same pressures, the same chemical composition, and so on, represented by this yellow region here. That's called a coarse graining region. And the logarithm of the volume in phase space, that's this volume here, multiplied by some constant, is the entropy. Why it's called S, I don't know, but there's probably a good reason for it. But that's the entropy. And here, you do that again, and you find that there are a lot more ways of doing it. And here, there are many more ways still. So the entropy is, roughly speaking, measuring the number of microstates which correspond to the given macrostate. And as this thing continues, the number of microstates gets larger, which is not unnatural. In fact, these coarse graining regions marked here don't differ very much from each other in the appearance, but that's misleading. If I could have all the dimensions that are actually present in this, which is a vast number, of course, then these volumes are likely to be absolutely stupendously different. So once it gets from this one into a bigger one, it's not likely to find the small one again, so it's going to get into a bigger one and a bigger one, so that you predict that the entropy goes up. There's nothing much to that. The trouble with it is that it doesn't work backwards in time. Suppose you said, what's the most likely way that you arrived at that configuration there? The same argument would say, well, it's much more likely that it started from a bigger volume than from a bigger volume. The most likely way is that it started as a mess on the ground. The glass all came together, jumped up, and the wine found its way into the glass, and it perched on the corner of the table. That's wrong, of course. What actually happened is somebody who'd been drinking a bit too much of this stuff was a little careless about perching it on the edge of the table. That's what really happened, and that's consistent with the second law. It was an even smaller region before, and so on and so on. So entropy, this is only a half an explanation. It tells you why it goes up into the future. It gives you the wrong answer if you try to retrodict the past. What actually happened is it came down, and it came down, and it came down, and it came down, until you came to the Big Bang.